This is what motivates our study. We start with the observation that a policy that enforces 2 degrees or that limits warming to 2 degrees will have to redirect investments massively, and that much of this investment is going to be financed externally, so it's often going to be intermediated finance. And financial intermediation introduces frictions. So it affects the interest rate, so now you can read, and it has effects on capital accumulation and allocation. And this is, of course, very important when we want to allocate funds to renewable energy and away from fossil energy. So the research question that we ask here is what the implications of such financial frictions are for climate policy. So we're going to look at the effectiveness of climate policy in a model that has such financial friction and see if we can draw conclusions for our policy design. And that's also motivated by the data that you see here, where low volumes of credit are associated with high interest rate spreads. And that goes to show that there is a clear correlation of the two. So in the following talk, in the continuation of my talk, I'll show you a climate policy model that we built without a financial sector, and then show the industrial organization's approach to banking, which we use then to integrate this into our model, and then we can discuss climate policies with financial frictions. There is literature that looks at this from different angles. One strand considers the cost of capital, which has been important because renewable energies are very capital intensive. So with high cost of capital, you can even see climate policy becoming ineffective and not triggering investment in renewable energy. On the finance theory side, financial frictions have been shown to have strong effects on investment. This is in the financial development literature. And in modeling, this has been taken up in DSGE models often, but not so often in the context of climate policy. Finally, there are some steps being taken to integrate financial questions into integrated assessment models, for example, into the DICE modeling framework by Nordhaus, or in different kind of modeling frameworks like stock flow consistent models. So here is the climate policy model that we're going to use. We have a very stylized model that knows households, consumer savers that provide funding for the rest of the economy. There is production of the consumption good that draws on energy, and energy comes from 3 sectors: nuclear, renewable, and fossils. Fossils use resources, fossil resources. That, of course, gives rise to CO2 emissions. It's a dynamic general equilibrium of this economy, and we have a government that sits on top of this and that we can use to numerically compute optimal policies. So if we impose a budget on CO2 emissions, this government can use a carbon tax to force the economy on this path. We have built and applied this for looking at technology policies. Now we're going to introduce the finance part. When modeling the banking sector, the finance sector, financial intermediation in this model, we want to capture a couple of contributions to interest rate spreads that you see in this figure, in the figure here in the middle. Namely, we want to capture that banks make profits. So we're going to have imperfect competition in our model, overhead and tax expenditure. So this includes all the administrative costs, the costs of managing the loans and deposits. That's captured in an intermediation cost function. And loan loss provisions, we have something similar in the model. We will require the bank to hold reserves, and this will also add to the banking spread. So the industrial organization's bank will attract deposits by setting or by paying a deposit rate on all the deposits. This will incur some costs of managing these deposits, and it'll keep reserves, a fraction of these. It'll earn money by providing loans and charging a loan rate on this, but screening and monitoring of these loans is again costly, and all of this in an imperfect competition setting. The underlying theory is going back to seminal papers by Klein and Monti, the so-called Monti-Klein model. It has been used in the literature, mostly in empirical literature, as the underlying theory when doing empirical studies of banking concentrations and imperfect competition in the banking sector. But there are also some recent extensions, theoretical extensions of this model. And it has been used in studies that link bank concentration to economic growth. So the last two on the slide, they use this kind of a model in endogenous growth frameworks to explain growth effects of banking competition. What does this look like? Banks maximize profits. Profits are the difference of earning on the loans and spending on the deposits. And a fraction of the deposits needs to be kept as cash reserves. Banks also take a position in the interbank market. So whatever they want to hand out in loans that they do not hold in deposits is what their position in the interbank market is. You can substitute this in, then you get this equation, and then for the perfect competition equilibrium, simple first order conditions, I show this here because this is very intuitive. You can see that the interest rate spread that you get from this is determined by the marginal cost of loans. That's the spread above the interbank rate, and likewise the marginal cost of deposit. That's how far you go below the interbank rate. When you introduce imperfect competition, you get the same equations basically, but you get this factor here that has the elasticity of supply of loans and the elasticity of demand for deposits, or the other way around, demand for loans, supply of deposits that factor in here, and capital N, which is the number of bank, which is a measure for the competitiveness in the sector. And this amplifies the spread that is otherwise driven by these marginal costs. We're back to the climate policy model with a single interest rate in the base case, and we now put in a banking sector here, so all the savings go to the bank. This is an extreme scenario. We do this to have like the strongest possible effects, but also because this way we can avoid portfolio problems in the model. And then the loans fund the buildup of capital stocks in the economy. This is an aggregate view of the results. Here we see in red the investment, the deviation from the investment in the base case in the model. Base case would be here at 0. And then with higher or lower interest rate spreads, you can see that investments are higher or lower. This is superimposed on data where Williamson has compiled interest rate spread versus investment data for the US. So you can see that roughly we have a similar reaction in the model than we see in the data. When we want to analyze what the effect of the interest rate spread are throughout the economy, we distinguish 7 partial equilibrium effects. I want to go through this quickly before I show you what we find in general equilibrium. You will assume here, this is the first point, that's the decision taken by the consumer, the savings decision, and if the deposit rate is below the usual interest rate, then the savings decision is to consume less. We see that the growth rate of consumption is lower. And we can show this analytically in proofs in the manuscript. Here I just want to point out these effects for you. Similarly, demand for capital falls when the loan rate is higher than the interest rate before we introduce the frictions. With lower capital, of course, aggregate output is going to decline, and that's going to decrease the demand for energy. So energy demand is down as well. But we see, because capital is getting more expensive, we see a shift towards a substitution effect towards energy. Output becomes more energy intensive. A really important effect is this portfolio effect, where we have here the share of fossil energy to renewable energy. And we can show that with these financial frictions, the energy portfolio will be biased towards the less capital-intensive energy source, which is the fossil energy. Finally, carbon intensity will increase as capital gets more expensive in the fossil energy sector relative to the resource, and the extraction dynamics is going to be slowed down. We see a slower growth of the resource price. Here you can see what happens in general equilibrium in the economy. You see that as a function of the interest rate spread, the deposit rate decreases and the loan rate will increase. If you look at the other prices in this economy, what's evident from this figure here that shows you the price for renewable energy, fossil energy resources, and the wage rate, is that all factors that are based on, that have capital as an input, they all become more expensive, and wages are the only price that falls. You can see that renewables in particular have a strong effect, and if we look at the unit cost functions here, that gives you an idea why this happens. This compares the unit cost function of fossil fuel and of fossil energy and renewable energy, and whereas the only determinant of the unit costs for renewables is the interest, the price of capital, you have the price for the fossil resource making up a large share that determines fossil energy prices. So any increase in the interest rate does not carry through as strongly. Consequently, capital demand falls in all sectors. And this is the result that we get for business as usual. And this would not be very exciting. This would be what we would expect here. When we look at climate policy, we get a more interesting result. This is cumulative emissions in climate policy with no friction. And we compute here a carbon tax that keeps roughly a 2-degree compatible policy. We keep this policy fixed and then increase the friction in the economy. What we then see is that while this first policy kept this policy target, we now see an overshooting of this policy. The carbon pricing the effectiveness of the carbon price is reduced in the beginning such that emissions are higher, and then as the friction becomes very large, there's a growth effect that is dominating then, and that is what drives emissions down. We can understand this when we look at the prices again, whereas before all these prices were rising, we now see that the price for fossil energy shows only the slightest increase. And if we look at unit costs, along with the price for fossil resource, we have the carbon tax here. Carbon tax price is this dashed line. You can see that it dwarfs the price for resources from business as usual. So with this high carbon price, any change in this interest rate becomes insignificant. And that is why the increasing price in renewables has such a strong effect. It affects renewables strongly, and fossil energy is not affected very much. This is the analogous diagram for capital demand, and now you see that capital demand is rising for the fossil energy, but also for the resource extraction. And of course, resource extraction is then what gives you the additional emissions in this equilibrium. We try to get estimates of the order of magnitude by isolating these effects. So we run scenarios where we disable and enable the friction in single sectors throughout the economy. I need to move quickly here because my time is almost up. But the message of this figure is that in bold here you see effects. I'm just going to go through one example. For the consumption growth rate, if we look at the contribution of the consumption decision, that is a 12% reduction of the growth rate. And likewise, you will see that the signs in the bold-faced numbers reflect the theoretical arguments that I showed you before. So anything we can do to counter this? This is the last figure I want to show you. Here you see, again, for the interest rate on the x-axis, the amount by which you need to increase the carbon price to stay within the budget that we've set. So for higher frictions, we need to set a carbon price that is up to 20% higher than the one that we would anticipate if we thought there was no friction in the economy. With this, I want to conclude. The main takeaway is financial frictions reduce investment and growth, but also cause an overshooting of the policy target, which necessitates a higher carbon price. Thank you very much.